Okay, welcome back to the second talk this morning. We have Professor Chan-Ho Kim from Jeonbuk National University. He'll speak on refined aspects of some Kolyvagin systems.
Okay, thank you very much. Thank you for the introduction and thank you for the invitation. I really enjoy this time and it's my first time to be in India and yeah, I love this place. Okay, so today what I want to talk about is the refined aspects of some Kolyvagin system. Indeed, it does not give you any information. So first, let me start with the anti-theme of this talk. So first, we will talk about some common features of the Euler systems, all the known Euler systems, I guess. So I have number field F and any a geometrical representation V and of the absolute Galois group F, and let me take the Galois stable lattice T. Then what people usually do is construct an Euler system, which are unramified coherence classes over a ramified abelian extension over F or T. So here I made a quotation mark for unramified because, for example, Kato's Euler system is ramified at P, but usually the same direction, the unramified, and prove its non-triviality by making the connection with the L value or derivatives when the analytic rank is law. This is the part of the explicit reciprocity law. Then apply the Euler system machinery, which we will more focus on later. And all this plane give us the upper bound of size or exponent of the Selmer groups or T-Sharp-Arbich group of the dual Selmer by this special L values we got in the step 2. And also a similar story goes over a relevant GP extension of the base field, which are nothing but the lambdatic version. This is what people usually do. So, and this Euler system machinery step involves the derivative construction, like cyclotomic unit, Kato's Euler system, Higgins points, or level-raising congruences following the Botorin-Ramon's bipartite formal system argument. So why do we do this? This process produces a ramified cohomology classes for the portion Galois representation, and you get more a ramified classes. We have more chance to get a bound of the dual Selmer groups. These class form a so-called the Kolyvagin system if you need some change if it is needed. And some Chebyshев density argument is involved because we need to choose a bunch of primes which are ramified. And by using them, we also use the global duality many times for each step. That's how the game goes. And the theorem is like this. So if Galois representation is large image, and if you have a non-trivial Euler system, and the bottom class is non-torsion, then dual Selmer group is finite. Or in the different situation, you may have the version like a Selmer rank is 1. So this is how game goes. This is the Mazur's diagram, which summarizes this picture. So we start with some algebraic treasure. It's the cyclotomic units, elliptic units, Higgins points, singular units, the source of all the Z elements, and making connection with the critical L value or via explicit reciprocity law or Gross-Jagier formula. And from here, building Euler system, we get Euler system is the unramified coherence classes over abelian ramified extensions. And take the Kolyvagin derivative process, we get the Kolyvagin system, which is ramified coherence classes over the base field. And by applying the global duality argument, we get a bound of the arithmetically interesting modules. That's how we make the connection between the critical L values and the Selmer groups. So this is the Bloch-Kato conjecture. And this picture works very, very well for decades, and also extremely fruitful. So it's natural to try to understand all the Euler systems in a uniform framework. And of course, the most difficult part, except the conjecture itself, is the construction of a new Euler system. So finding good Z elements and proving the family of these Z elements really forms an Euler system and proving explicit reciprocity law. And if we manage this problems for such motive, and we get the non-trivial result on the Bloch-Kato conjecture for that motive. So this method, the methods constructing new Euler system is being developed by Eric Orban and the Raphael Jarvis and San Giovanni Skinner, and independently by different ways. So until now, so this is exactly what I will not talk about. And in this talk, I'd like to go to a bit different direction. What do I mean? So I'd like to focus more on the Kolyvagin systems rather than Euler system. Also, I'd like to utilize each zeta element, the own characteristic of each zeta element, which may not be a common property of Euler systems. And also try to develop the connection with other contexts. That's what I want to do in this talk. And here are 3 menus. First one is the Higino points. So this is basically grew up from the discussion with Min-Hyung Kim. So here, what we want to talk about is how to utilize the so-called construction of Selmer groups. And we will also talk about the Bloch's special cohomology classes. In this talk, I would like to call it Bloch's zeta elements or adjoint semi-stable elliptic curves. Basically, what Bloch did is in his earlier paper, like in 1991, he proved the congruence number annihilate the adjoint Selmer group by using these special cohomology classes. But it does not give us a exact bound. So that was the kind of the so-called gap of the Wiles' first approach to the Fermat's last theorem. In this talk, I will talk about how to go a little bit further. And the last but not least, is joint work with Gugino in progress. So we will talk about the relation, indeed, how the Dirichlet cyclotomic elements can be used for Bloch-Kato conjecture, and this is of course natural, but I'd like to emphasize the connection with the Eisenstein ideals. This is the course menu for today. This is the kind of omnibus movie talk. So first, we go through the Higino points. So let E be an elliptic curve over Q and conductor N, P is larger than 3. Let me just assume that Gun reduction prime for convenience. But we will always assume this torsion Garo representation is surjective. And let K be an imaginary quadratic field satisfying the generalized Higino hypothesis relative to this conductor N. So we'll always have the root number E over K is -1. So for a positive integer N, K bracket N means a ring class field of K of conductor N. And let me just assume that everything in this slide, let me assume we are in the classical Higino hypothesis for convenience. Now, all the prime divisors of N splits in K over Q. Then we can decompose N as follows. N is the mathfrak N times its conjugate in OK, such that the OK quotient by mathfrak N is nothing but G mod NZ. And in this case, any positive integer N, we consider the CM point Xn, which is defined by this 2 pair in X naught N in terms of moduli. Here, the C quotient by ON is a G plus N OK. And this mathfrak N sub N is the intersection between the mathfrak N and mathcal N. And by the complex multiplication theory, we know it's the field of definition. It lies in the K bracket N. And fixing a modular parameterization, then we get a point in the elliptic curve. We call it the Higino point of conductor N. Okay, this is the thing we know. Sorry. Okay. So following the construction, we have the collection of Higino points varying N, and we assume that N is co-prime to N, the conductor and the discriminant of K. It may come from Shimura curve also, so it doesn't matter too much. And it satisfies the following, the so-called distributional relation. And so this relation is so having this relation is so-called the Euler system in this case. So all the Kumar images of this Yn forms a Higgs point Euler system. And these all come from the points. So these are like unramified Kummer's classes over a ramified abelian extension. These are all the standard things up to now. Now we move to the Kolyvagin system. So let me say the L is a mod P to the K, it's a mod PK Kolyvagin system if it does not divide 2P and DK, and L is inert in K, and L plus 1 is congruent to modulo PK, and AL, the ALE, is also congruent to 0 modulo P to the K. And mathcal NK is a set of the square-free product of mod K Kolyvagin primes. And for each n in the mathcal N1, we define the In as the ideal of ZP, generated by actually this. So basically, if you are not familiar with this kind of notation, you can just think this is just PK. So for each n, we define the kappa n Higgs as follows. So take the Kolyvagin derivative to the Yn, and to make a summation over this the conjugate over the Hilbert class field. It turns out that, and take the mod ion reduction. It turns out that then it is an invariant under G. G is nothing but the Galois group of K bracket N over K. So using the Kumar map from here to here and take the restriction map, the inverse of the restriction map, we get a class in the H1 K E bracket IN. So we have the Kumar's class in the torsion Galois module. And also, furthermore, one can prove that this kappa n is actually lies in the n-transverse Selmer group. So transverse is introduced in the Kurihara's talk about the Rubin-Rocher condition. And there are some technical issues about the constant multiple, but we will ignore that today. Anyway, so these lies in this cell n. So these classes are expected to be ramified at the primes dividing n in general. And these classes satisfy so-called Kolyvagin system relation, which we will not discuss too much. Anyway, the collection of this kappa n is called the Higgs point Kolyvagin systems. And denoted by just bold kappa Higgs. And in fact, when we proceed the Euler system argument, we always factor through like using this guy. So the natural question is this non-zero? And if so, what can we do with this? So here's the groundbreaking theorem everyone knows in this room, I guess. So the work of Grosjean and Kolyvagin. So when the analytic rank is small than equal to 1, then the rank part of BSD conjecture is true, and T-sharp of each group is finite. And also strong converse to the above theorem is now widely known by work of many people. I'm sorry about missing all the names. There are so many people do the P-converse these days. So the converse means the following. So if the Selmer rank is 0 or 1 for certain P, which basically where the Higgs point main conjecture holds, then the analytic rank is 1, 0 or 1. So if the analytic rank 1 case, the non-triviality of this whole system is automatic, because the kappa 1 Higgs itself is non-torsion via Gross-Jagier formula. So the Euler Kolyvagin system argument cannot be vacuous, so it just works. And what can we say about the higher rank case then? And can we really sure this kappa Higgs is actually non-zero or not? That's the conjecture of Kolyvagin. So in order to deal with the higher rank case, Kolyvagin formulate the following conjecture, so-called his conjecture A, not Koch-Sujata conjecture A. It's like so what he conjectured is a Higgs point Kolyvagin system itself is always non-trivial, which means kappa Higgs n is non-trivial for some n at least. Indeed, it is the first conjecture of his series of conjectures. There is also conjecture B concerns the same question, but admitting like a residual reducible case, even including the P torsion is actually non-trivial. That case is also included. And conjecture C focuses on the relation between Tamaga defect and the minimal valuation of the whole Kolyvagin system. This is now known as a refined Kolyvagin conjecture. And conjecture PD, the final one, is basically equivalent to finiteness of P part of Chow. Okay, and why he made this conjecture is what Kolyvagin's conjecture actually tells us about the higher rank case. Before stating the theorem, I need to introduce some notation. So under his conjecture, what Kolyvagin did is that he described the module structure of this Selmer group over Q, not necessarily over K, in terms of kappa Higna. And yeah, yesterday this notation appears. Nu n is the number of prime divisors of n, and here are like a number of the numerical invariants associated with kappa Higna. The old kappa Higna is the minimal nu n, which like a kappa n is non-zero. And each kappa n, we measure the valuation, p valuation, by checking the maximal j in the pj cell n, so maximal divisibility. And now the partial zero is nothing but the divisibility of kappa, the base point, base Higginson point. Partial I is all similar to the yesterday's business, is the delta n business. Partial I means the minimal valuation bearing all n, satisfying the nu n is exactly I. And partial infinity kappa Higna is basically the minimal valuation of the whole kappa n. So if you are not familiar with this notation, like you can think that this order is really behaves like a vanishing order. And partial zero is more like a reading term. And partial I, you can regard as an ith tail expansion in kind of. And partial infinity should play the role of the Futch vector. So here's the theorem of Kolyvagin. So suppose that E bracket P is surjective and K satisfies the relevant generalized Higginson hypothesis. In particular, the Selmer corank is larger than its quadratic twist. And this is, yeah, we can always make like this for higher rank case, of course. If Kolyvagin's conjecture is true, then following statements is true. So Selmer corank is exactly detected by this vanishing order of Higginson point Kolyvagin system. And if we write this, the quotient by maximal divisible part, so this is finite group, which should be Chow. And this exponent EI is exactly captured by this invariant. Oh, I should put the square, sorry about that. This everything appeared as a squares because of the Cassel state pairing. Anyway, so structure of the Selmer group is determined by non-trivial Higginson point Kolyvagin system. And as we've seen yesterday, so similar structural theorem are developed by Kurihara in terms of delta n, which I call Kurihara numbers. And Major Rubin also did this structural theorem, but for p-strict Selmer groups, not Bloch-Kato Selmer groups, in terms of Kato's Kolyvagin system independently. And as you've seen, the Kurihara structural theorem is more suitable for computation, but one interesting virtue of Kolyvagin's structural theorem will be discussed soon. And it's natural to ask how much is known about the Kolyvagin's conjecture after Wei Zhang's seminal work. I feel very sorry about missing many works, but there is a reason to say these two. Like I will say why. The first one is the recent theorem of Burungale, Castilla, Skinner. And let E be an elliptic curve of Q and P is larger than 3, good ordinary reduction prime. And there are some certain conditions, but basically, what I want to say is that there exists imaginary quadratic field K and such that the Kolyvagin's conjecture is true for this triple EPK. And by developing the connection between the main conjecture, which is a kind of behave like a vertical direction, and the non-triviality of the corresponding Kolyvagin system, which varies horizontally, but they have the deep connection, and we obtain the following results. So this is due to the Burungale, Castilla, Skinner, and myself. So under the same condition, basically Kolyvagin's conjecture is true. So this work of BCGS also covers the residual reducible case, but still need the EKP bracket is trivial. And my approach basically gives an equivalence between the Huguenot point main conjecture, but only localizes one prime, so one height one prime, which is nothing but the augmentation ideal, and this Kolyvagin conjecture that basically equivalent. So this is one of our key observations. How about the supersingular case? So there's a theorem of Castellan-1, which works for semi-stable elliptic curves. Basically, there are several conditions that what I want to say is simple. So I have a semi-stable elliptic curves, and P is larger than 3, good supersingular reduction prime. Then we can find an imaginary quadratic field, which make the, in this case, signed version of the Huguenot point main conjecture is true. And even more like a general Shimura curve setting, like a signed conjecture, signed Huguenot point main conjecture is true up to a power of P. So this is the work of Castellan. And what I could do is developing the connection more. And under the same condition, I could prove the Kolyvagin conjecture is true in the supersingular case. And of course, there are many people's other work. I didn't say the name. I'm really sorry about that. But here's the reason why I mentioned why I mentioned only these two among others. So one reason is, the biggest reason is this result does not require any tame ramification hypothesis. This is exactly what I need for a new application. Okay. So the nature of the proof of Kolyvagin structure theorem is different from other structure theorems. As far as I understand, this is mainly because these kappa and Huguenot not only bound Selmer groups, but also generate Selmer groups. So we call it the Selmer construction. This is one of the interesting and peculiar aspects of the Huguenot points. Under the large image assumption, we have the embedding, this H1K EPK to the same one, but the Galois module gets bigger, EPK plus 1. We have an embedding under the large image assumption. So under this embeddings, we can regard this kappa and Huguenot, each kappa and Huguenot, as an element of the H1K EP bracket. So now it's a discrete Galois module, not compact one. Although we just play with a Galois cohomology classes usually lies in the compact Selmer groups. So here's one of the theorem of Kolyvagin in the middle of the proof of his structure theorem. So suppose that this EP is always surjective and K satisfies the Huguenot hypothesis, and the rank of the original one is larger than its quadratic twist. And if Kolyvagin's conjecture is true, this Selmer groups actually lies in the module generated by all the kappa and Huguenot. And then what can we do with this Selmer construction? And this Selmer construct says that every non-trivial element of SHA splits in a ring class extension of K. Because all these comes from the points in some ring class extension of K. So this is a different type of controlling K-Shaprovich groups and leads a new application. So let me recall the theorem of Cipriani-Wiles on the solvable points on genus 1 curves. So what Cipriani-Wiles proved is if we start with a genus 1 curve, smooth projective curve over Q over genus 1, such that all the local points are non-empty, including infinite place, of course. If it's Jacobian, is semi-stable, then C, oh, sorry, it's about this typo. C admits a point in a solvable extension of Q. Now we try to recover this theorem as much as possible. And now we record the corollary of the works on the Kolyvagin's conjecture. So this is exactly what I wanted to say. So I start with a semi-stable elliptic curve over Q, and P is larger than 3, Gunn reduction prime, such that EP is now only say irreducible because it's under the semi-stability assumption, surjectivity and irreducibilities are equivalent, in particular in P is larger than 3. And there exists a relevant imaginary quadratic field K such that Kolyvagin's conjecture for this triple is true. Then here's the thing icon up to now. So combining this corollary with the Selmer construction, we partially recover this Cipriani-Wiles theorem. So almost same, but we have one more assumption. So C is a smooth projective curve over Q, genus 1, all the same. But I cannot control the Taysha-Farvich group, non-trivial Taysha-Farvich group elements whose order divide the conductor. So I should assume this, like a SHA of this J over Q bracket N is 0. Then I have the same conclusion. And how to get rid of this like a unfavorable condition? And we just need to prove the Kolyvagin's conjecture for elliptic curves with a multiplicative reduction, also without imposing any time ramification hypothesis. If we finish that, and we basically recover the Cipriani-Wiles theorem. And this is the multiplicative case. Is ongoing joint work with Ashay and Francesca and Minhyung Kim. And the Cipriani-Wiles, so this approach using the Selmer construction gives us one interesting criterion for finiteness of SHA. So here's the statement. So let me start with the semi-stable elliptic curve, good reduction prime, and if it's irreducible, which means surjective, then let me assume that we could find the imaginary quadratic field K such that Kolyvagin's conjecture for this triple is true. Then all these three statements are equivalent. The third one is the finiteness of the P part of SHA. The first one is basically where this kappa n lies in the Selmer groups. The kappa n should lie in this image of the model Weil group in the Selmer groups. So, but if we did not take the mod IN reduction, what first statement says is derived Higginson point itself actually lies in here. So this second statement basically says to us like if we believe the finiteness of SHA, these points approximate the model Weil group modulo P to the K. So, and I think this statement is not observed in the approach of the Cipriani-Wiles. So this is the first part of my talk. Okay, let's move on. Any question before, maybe I can collect the question in the end of the talk. The second, let me change the subject. So let's go back to the mid-80s or early 90s. Like after the work of the Fry, Serre, Ribet, people recognize the semi-stable Shimura-Taniyama conjecture implies the Fermat's last theorem. And at the moment, like in his earlier attempt, Andrew Wiles tried to construct an Euler system for symmetric square representation for semi-stable elliptic curves, extending Floch's special cohomology classes. More specifically, Floch constructed the collection of, indeed, he constructed a family of cohomology classes, not only one, and applied a part of the Euler system argument to obtain the annihilation of the adjoint Selmer groups, which bounds only exponent. And we call it like a Kolyvagin, Floch Z elements in this talk. But what Wiles wanted to have is the exact upper bound of the size of adjoint Selmer groups, not just an annihilation result. So it turns out that the construction of the Euler system did not work well, but they found a new method, so-called the Taylor-Wise system. Everyone knows now. So they proved the Fermat's last theorem, and Taylor-Wise system argument itself becomes the essential ingredient in the development of Langland's program. But question still remains. So after that, the construction problem itself remains a very hard problem. And Major and Weston pushed this Floch's construction further to develop the theory of the so-called the partial geometric Euler system of depth eta, but it still did not give us like a exact bound. And the question is, the Euler system approach to the modular theorem is really impossible. And now there are new alternative construction of Euler system for symmetric square or adjoint, thanks to Eric and the Raphael Jervis and San Giovanni Skinner. So let me change the question a little bit. Is Wiles' original approach based on the Floch Z elements really impossible? This is, and another question is due to Hida here. So another motivation comes from the secret question in Iwasawa theory. Around 1960s, Iwasawa himself proved the cyclicity of certain classical Iwasawa module over the Iwasawa algebra, as well as the main conjecture under the Kumar-Van Diver conjecture. He also proposed an interesting question of the cyclicity around the 1980s, and later Hida studied non-abelian analog of this question, namely cyclicity of the adjoint samogroups over the deformation ring, and he also asked the same cyclicity question without considering any deformation. So this is the main question. When do the adjoint samogroups of elliptic curve over Q become cyclic? And we presented partial results on these two questions. So let's review the Wiles strategy. First, start with the modularity of Mount representation. So Ramanujan's tunnel theorem, stereo conjecture was not known at the time, of course. Modularity lifting theorem and 3-5 trick. And in the modularity lifting theorem, there are two steps, minimal one and extension to the non-minimal one. And the minimal one is where the Taylor-Wiles system argument is crucially used. And my guessing is that Wiles first tried to get this minimal modularity lifting theorem by constructing an Euler system extending flux zero elements. Let's recall the what flux theorem. So E is always the semi-stable modularity curve, so we do not assume the modularity here. Over Q of conductor N, and P is larger than 3, good reduction prime. Rho bar is always subjective, and N is now, we assume the minimal level in the sense of the Serre conjecture. And degree of phi is the degree of minimal modular parameterization, and adjoint representation is here. This is a discrete one. And Flock proved this. Like if you have the adjoint representation, if you multiply degree of phi, you get 0. So in particular, this Selmer group is finite. But what Wiles actually wanted to bound is he wanted to have like this type of result. Actual length is smaller than the valuation of degree of phi. So let's recall some like a notation. So Sim2 TPE is a symmetric square representation of Tate modular of E. And then there's a duality, of course, like a symmetric compact one taking like a Kolyvagin dual and taking a Tate twist, and we get the adjoint representation, discrete one. And what Flock constructed is that for many infinite many prime L, all but finite many prime L, he constructed so-called the CL, which is ramified at L in the symmetric square Selmer group, a compact Selmer group. And all the other primes, it is the satisfied Bloch-Kato local condition, so unramified or crystalline at P. But if we like restrict to L, then it basically detects the degree of phi and some extra data, but we will ignore that later. And this cell L-RAL means the Selmer structure, the Bloch-Kato Selmer structure basically, but only change the local condition at L as a relaxed one. And localization map is just restriction map, and S is we add a singular quotient. And alpha L beta L is nothing but the roots of the Hecke polynomial at L. So, okay, so we have infinitely many cohomology classes which ramifies at infinitely many primes. But this is not the one we want to proceed the Euler system argument, Kolyvagin system argument. We want to have Cn, which is the ramified at many primes simultaneously to get bound size. So more precisely, if we add like one more ramified primes in the cohomology classes, we have a chance to annihilate one more generator of the dual Selmer groups, thanks to the global duality argument. So here's the one, okay, so remark on the Euler system versus Kolyvagin system. So Euler system, as I emphasized many times, basically unramified over ramified extension, and Euler factors are basically detected by this norm compatibility. And I usually consider it as a cohomology conversion of the zeta function. But Kolyvagin systems are basically ramified classes over base fields in torsion coefficients, and usually obtained by derivative process, but not in this case, like you will see later. And this should be viewed as a cohomological version of Taylor expansion of the zeta function. Okay, so now I have a bunch of CL, but I can't make CN right now. What should we do? This is, my guessing is this is where the famous gap occurred. So this is the picture. This is the Euler system, Kolyvagin system, get a bound, and we get more ramified coherence classes here. Then we get the more strict Selmer groups in the dual side. So if we make the Selmer groups where the Kolyvagin system lies in bigger and bigger, then the dual Selmer groups get smaller and smaller. This is how picture goes. And around the year 2010, people including Major Rubin, Takamichi Sano, David Burns, Hirotaro Sakamoto have recognized another system called the Stark system. As the name suggests, the motivation comes from the Stark conjecture and Rubin's integral refinement, not basically related to the adjoint business. In the rank 1 case, the Stark system is basically isomorphic to the Kolyvagin system. There is an explicit map. And the key idea was, so put the whole collection of the flux general elements varying all L into the framework of Stark system. And try to construct a Stark system from scratch. And this process is surprisingly simple and works, but we should pay some cost. So because of one caveat is that because of this cost, we will not have a new proof of the modularity theorem yet, but we will see some equivalence statements. So here are some preliminaries. So K is an integer. Let me say this is this case, the Kolyvagin's prime for this version. When I say the flock prime, it is not P, it's a good prime, and it is congruent to modulo P to the K, congruent to 1 modulo P to the K, and AQE is not congruent to plus minus 2 modulo P. This latter condition tells us like an arithmetic probability with Q acts like this, alpha 0, 0, alpha inverse, and alpha square is not congruent to 1 modulo P. And for this K flock prime, so the singular quotient of local cohomology is basically free of rank 1. And for this flock prime, this inequality, so the valuation of the localization at L of the CL becomes equality. So because of degree of phi is related to adjoint L value, thanks to the formulas of Shimura and Hida, it's reasonable to say this statement is explicit reciprocity law. Now we do some preparation for Stark system. So we first need to fix one flock prime, L, and we will not change this. And consider the Selmer triple, the symmetric square representation, and L relaxed Bloch-Kato Selmer structure, and all flock prime except L. And this triple satisfies all the, like a working hypothesis for Stark systems. It is not that hard to verify them. And here's the formalism. So fix on N is the product of the like S K flock primes, Q1 to QS. And Wn is the dual of this local singular quotient. And Yn is wedge product of Selmer group and Ln relaxed and tensor and wedge product S and Wn. And for m dividing n, there are Cartesian square from the Ln Bloch-Kato Selmer embedded to Ln Bloch-Kato Selmer. In the Galois modules are same, and product of the localization also embedded like this. This Cartesian square there is a Cartesian square like this, and there's a canonical map psi nm from Yn to Ym attached to this above square. Although we not go through the definition of this guy, but we will explicitly use it in the key computation later. It is known that this psi nm is transitive, which is good for us. Okay, so now we can give a definition of the Stark system. The Stark system is the compatible under this transition map. So taking the inverse limit of yn, and the compatible family of this element is called the Stark system. And our Selmer triple satisfying this rigidity property. So rank 1 Stark system is free of rank 1, and also there's an isomorphism between the rank 1 Kolyvagin system. So this free of rank 1 property says there must be a Kolyvagin system or Stark system at least. So this statement was the very starting point of this project. So okay, here's some important properties of Stark system. So when I say the Stark system primitive, then its image in the mod P is non-zero. And this primitive Stark system will generate this free of rank 1 module. And what Major Rubin proved, if the Stark system is non-trivial like Kolyvagin system, he could detect the exact bound. And this weird notation is the basically phi, partial phi, whatever, is the minimum valuation of the whole Stark system. So if it is primitive, then this L strict Selmer groups, because the Selmer structure was the L relaxed one, so this Stark system will bound L strict Selmer groups. And the size will be exactly given by the order, the divisibility order of this first class. Indeed, actually this whole system, if it is non-trivial, will determine this structure of the L structure Selmer group. L strict Selmer group, sorry. And but we want to bound just Selmer groups, not L strict one. So by global duality, we can measure the difference. And this difference is exactly captured by sending this to the restriction as an image of the singular quotient. So Weston's explicit reciprocity law will play the role. Then, okay, now how to construct that? We just have a bunch of CL, but not CN. The very first idea coming for me was that the Stark system made from the bunch of the wedge product. So my first idea was, why don't we try this, taking a wedge product bunch of these guys? And here, I testedly fixed the order of the primes dividing n here. Okay, I just play with this guy. And of course, it does not satisfy the compatibility relation in the definition of Stark system. But fortunately, it does not go too far. So I just compute the image under this transition maps. Then thanks to the local condition of flux zeta elements, I only have the constant term. And the remains as almost same. And by iterating this computation, I just recover CL, and a bunch of constants are here. So from the key computation, it is natural to define this like our candidate. So I add a question mark here, flock question. It's natural to define like this. And for all m dividing n, it satisfies this by definition. So it forms a finite Stark system by definition. So in other words, it's a Stark system for Selmer triple, but primes are very restricted right now. So only finite set of primes dividing n. So these type of things are observed in the Euler system of Gauss sum. So now we just start with this, we get a finite Stark system, and what can we do further? And here's another important observation. So because of rank 1 property, this finite Stark system naturally extends to the whole Stark system. So this extension is not a miracle. It shows the strength of the rigidity of the Stark Kolyvagin system. So we have the bona fide, the Stark system, And this extended Stark system determines the L-strict Selmer groups and detect the size of the just the Selmer group by global duality argument, as discussed before. Everything is good up to now, but time for paying the cost. The bottom class of this Stark system has this constant in front. And so because of this constant, it is unclear what kind of bound we actually have. So we need to investigate the minimal valuation of the whole Stark system. Equivalently, we need to compute the primitive one from this extended one. So analyzing the global duality argument precisely, so we could compute the primitive one, and we call it a Bloch-Stark system. And very unfortunately, the constant term of the bottom class involves the length of the adjoint Selmer group itself. So it becomes the dumb, but like it just shows that there exists a primitive Bloch-Stark system. The precise formula, I can compute this. The bottom class looks like this. The Bloch class times something. And all the other terms, basically, I can give the explicit formula from the Bloch class. But the problem is that this lambda is nothing but the length of the Selmer groups. So we start with our choice was the very arbitrary. It makes sense for every n. So what's the main theorem then? So what we could prove that there exists a primitive Stark system coming from Bloch set of elements whose bottom class is constant multiple of CL. And one interesting part is this Stark system, I do not know this Stark system actually comes from the Euler system or not. I have completely no idea. And another thing is the equivalence statement. So the following are equivalence. This constant multiple is periodic unit, then is equivalent to the minimal modular lifting theorem. And this is also equivalent to the Bloch-Kato conjecture for adjoint motifs. So in particular, we admit the Taylor-Wise system argument, all these statements are true. So we do not get a new proof of Fermat's last theorem, but we could make the connection between the flux one and the modularity theorem. And also, a Taylor-Wise system argument not only prove the modular lifting theorem, also completes Weil's initial approach to modularity. So this is and the second one is now go back to Hida's question. So now we assume the first one. So I admit the R equal T, the constant multiple is periodic. And if the flux class is not divisible by P in this compact Selmer group, then this adjoint Selmer group should be cyclic. And it should look like this, GP quotient by degree of P. So this type of results can be viewed as a structural refinement of Bloch-Kato conjecture. And all this business will generalize to the higher weight case in this ongoing joint work with Yokoro Sakamoto. And the question is, of course, can we upgrade these structures and constructs by removing the constant multiple? That's a natural question. It will give us a new proof of the modularity lifting theorem. So this is the end of my second part. And now I move to the Eisenstein ideal. It's a completely different setting again. Sorry about that. This is ongoing joint work with Gugino. So what we want to do is that we wanted to try to understand and generalize the results of Preston-Wake on the equivariant Bloch-Kato conjecture for QK, where the Q is even and larger than 2. So let me fix the setup. P is larger than 3 prime, and K is even number, larger than 4, and P minus 1 does not divide K. And L is a prime not equal to P with L is congruent to 1 modulo P. This is the major prime level N in this talk. And T superscript is the cospitral quotient of Eisenstein-Haeckel level gamma naught L over ZP. And I naught is the Eisenstein ideal. And in his approach, the one key object was the derivative of major Tate or Stickelberg elements like this. So Cusi prime MT is some constant, and BK A over L times discrete log L of A. So BKX is nothing but the Bernoulli polynomial. Log L is discrete log. And it makes sense in the G mod PZ, so we are fine. So this can be viewed as a higher rate analog of the Meros number or higher annihilator due to Miyawaki. And where does this derivative come from? In his approach, the derivative appears as the constant term of derivative Eisenstein series, which is constructed as follows very briefly. He constructed the certain two group ring valued Eisenstein series, such that one has constant term in the Q expansion at infinity, like this, so half of this, like a major Tate element or stickable element, and the other has the zero constant term, and compute their difference in the group ring quotient by P and all the higher degree term. That's how he get the derivative. And using this, what we prove is this is non-zero mod P, and the Eisenstein ideal is principle, the equivariant Bloch-Kato conjecture or QK over this group ring holds. And indeed, this statement itself is not new, and even slightly weaker than the known. The example is the work of Greite-Popescu. But his approach contains an interesting argument regarding the Eisenstein ideal. And indeed, he proved the reducible R equality theorem in conditions in the theorem that this non-zero in principle is related to behavior of T naught. What he also proved is this Hecke algebra is just ZP is equivalent to derivative is non-zero, and the Eisenstein ideal is principle. So further, in his argument, this isomorphism is very essential because it is used to lift the mod P to the K modular form to the characteristic 0, 1 uniquely. And after having this characteristic 0, 1, we can apply the Libet's lemma to get the correct Kolmor's classes. One natural question regarding the Eisenstein ideal is, okay, what happens when the level becomes square-free? What I mean is that when I say the square-free level, it will always, all the prime divisor will be congruent to 1 modulo P. And in this case, the Hecke algebra is very unlikely to be isomorphic to ZP in general. In particular, we do not expect the principality of this I naught in general anymore. So definitely we are not able to proceed the race argument directly. Okay, what about this non-triviality assumption? What can we say more? Mimicking the elliptic curve case last time, and it is natural to consider another delta Kn. I can just define like this. So same constant term. Now Bk A over N, this will play the role of the modular symbol and the product of a bunch of the discrete log and taking mod P. So this one should provide the generalization of this like higher weight analog of the Meros number. We certainly expect this one should arise as a constant term of more complicated Eisenstein series. And another observation is this number should be related to an Euler-Kolyvagin system. More precisely, it should be the image of a Kolyvagin system under the torsion variant of dual exponential map. That's the Dirichlet cyclotomic elements as far as I see. So we start with the cyclotomic units and making the Sula twist, we get a homology classes. So I do not go through all the things. The key part is we get the correct Euler system from the cyclotomic unit from the Sula twist, and it will give us the connection with the derivative major Tate element, something like that. So C1K zeta n lies in this atomic homology with the coefficient, the torsion coefficient with a twist by 1 minus k. K is always the even, and bigger than 2. So we have this actual cyclotomic element in the characteristic 0 coefficient. And it forms an Euler system, it is well known. So this is an Euler factor. And this forms an Euler system of Dillon-Soule cyclotomic elements. Now here's the connection. So I have the this Dillon-Soule element. Oh, sorry. So I still have 3-4 minutes. Okay. Yeah. Take the Kolyvagin derivative and push to the restriction and take the dual exponential map. And we should compute the image of the integral image of dual exponential map. But let me ignore that. It's not that hard for this case. Basically, mod P is same as the delta KL up to some uniform constant. And we are in the moment to generalize this computation to general N. We will do it soon, I guess. And after finishing the computation, we are able to utilize the major Rubin's Kolyvagin system. So we expect the following application. And all these are equivalent and all are true. First one, Iwasawa main conjecture. It is proved, we know. And the Kolyvagin system of Dillon-Soule cyclotomic elements is primitive, which means like a non-trivial modulo P. And the family of this delta Kn is also non-trivial mod P. So some delta Kn is non-zero mod P. And this Bloch-Kato conjecture, kind of Bloch-Kato conjecture without without L function is true, which count the size of the strict Selmer group, P strict Selmer groups of QP mod ZP twisted by K, is captured by the bottom class of this Kolyvagin system. And we also have this Bloch-Kato conjecture with L function. The Bloch-Kato Selmer groups of Q, the discrete Galois module twisted by K, is this one can be ignored, I guess. So it's same as the P valuation of K times zeta 1 minus K. So this is the progress. So this is kind of refinement of the Wake's theorem. So comparing with the Wake's theorem, what we've done is that we only need the non-triviality of this guy. And what do I have? I have the cyclicity of this Selmer group, like this. And we do not need like a principality of I naught. But also, like an equivalent Bloch-Kato conjecture follows. It's this equivalent refinement. We can utilize the argument of Greiter properties Q. And so this is the thing I got. We will get, yeah. So this is everything I prepared. Thank you very much.
Questions?
Oh, sure. Okay. I think over yeah, but I think the Bloch-Kato in their paper, like they made some twist and they proved it, I guess. We can talk later, I guess. Anyway, yeah, the equivalency itself is definitely fine. Yeah. Sure. Yeah. Sorry. Yeah. Okay. Yeah, I have no idea. Yeah. I mean, now it's Eric and Leffler Jarvis and so. I mean, I just want to know where. I mean, of course, the Flock just constructed the algebraic cycles, and he made this ramified classes. But I just wondered, so we start with the derivative classes, right? So I first felt it's a bit strange because I first believed every Kolyvagin system should come from Euler system, but it is not in the case. So I just wonder. I just have no idea. Yeah. Oh, I have no idea. Oh, that's the thing I don't know very well. Maybe we can talk more. Yeah.
Any other question?
Yeah.
You had these delta KLs, which were, you mentioned were analogs.
The last one?
You mentioned they were analogs of Merrill numbers. In terms of, yeah. So do they also control the spill rank of the Hecke algebra?
That's the thing I really want to know. It's like, I mean, so we try to do that. So like so if the problem is like, if we go to the Eisenstein ideal side, like everything becomes much more complicated. So like, for example, like in Preston's argument, like he used there some lifting and apply the Libet lemma and get a Kolmor's classes, all the business goes well. But in this case, we cannot apply the Libet lemma in general. So like it's hard to do some Eisenstein ideal business. It's just complicated to me right up to now. Yeah.
So the reason I ask is, so in the weight 2 case, the Merrill number not being, or this analog not being 0 mod p is the same as the cuspidal rank being 1.
Yeah, but I have no like expectation at all. Yeah, but
that's equivalent, I think, to the Eisenstein ideal being principle.
So
because like at the end you had this hypothesis that
mm-hmm.
your analog was not this delta KL was not 0 mod p.
Yeah, that's 0 mod p. Yeah,
but maybe that implies that the Eisenstein ideal's principle.
We are in the progress. Like I should talk with the Kyujin. Like he is more like he is more familiar with Eisenstein ideal. But like, yeah, we in that business we got stuck many times. Like, yeah, it's just too complicated to me. Sorry. Yeah.
Any other question? Okay, let's thank Chan Ho Kim once more. Yes.